Hello everyone, my name is Poria. Today I'm going to talk about our recent work on adaptive knowledge sharing in multitask learning for improving low-resource neural machine translation. This is a joint work with Ray Bontyne and Reza Hafari, my supervisors at Monash University. Here is the roadmap for this talk. I'll start with an introduction and background. Then we will see the proposed method for adaptive knowledge sharing in multitask learning. After that, we have experimental results and analysis, and finally a conclusion. As you may know, neural machine translation is notorious for its need for large amount of bilingual data to train a model with a reasonable translation quality. But for some, this is particularly inconvenient for some language pairs which we don't have enough parallel training text. Now the question is that how can we compensate the lack of bilingual data? One idea is to use linguistic resources and train one model for all of these tasks using multitask learning. In machine learning, multitask learning is an effective approach to inject inductive biases to help improving the generalization of the tasks. Here our main task is translation. And for the auxiliary task, we use semantic parsing, syntactic parsing, and named entity recognition. We can have a separate encoder-decoder model for each of these tasks. So, for example, here we have one model for machine translation. We can have another one for semantic parsing, syntactic parsing, and named entity recognition. Here is the high-level architecture of the multitask model. The input is a sentence along with the task tag. If the task tag is translation, the output would be the translation of the source sentence. If the task tag is semantic parsing, the output would be the semantic graph of the source sentence. For the internal architecture, as I mentioned before, we can have a separate encoder-decoder model for each of these tasks. But if we want to share knowledge between them, we need to share parameters between them. One idea is to share component between them. For example, we can share the component. We can share the encoder. So in this case, we have one encoder and 4 different decoders. Or we can share the decoder, or we can share both of them. In this case, we have one encoder and only one decoder for all of the tasks. But each component has its own duties, and it's maybe better to share a fraction of parameters inside each component. So each component has its own task-specific parameters and also shared parameters. The idea here is the idea is based on using deep stacked encoder and decoder. In this model, they use multi-layer encoder and multi-layer decoder, and some layers in the encoders and in the encoder and decoders are shared. For example, here 2 layers in the encoders are shared, and each task has its own parameters for the other layer. This partial parameter sharing lead to the better result than the full component sharing. But the problem here is that when we share the parameters among all of the tasks, it may cause task interference, because sometimes we have some commonalities among subsets of the tasks and not all of them. And now we want to see that how we can address this issue by using adaptive knowledge sharing in multitask learning. As I mentioned before, when we share the parameters of recurrent units among all of the tasks, it may cause task interference or inability to leverage commonalities among subsets of tasks. When we share the parameters of recurrent units, we in fact share the knowledge for controlling the information flow in the hidden states. And for addressing the task interference issue, the idea here is to use multiple experts in handling different kinds of information and adaptively share these experts among the tasks. For doing so, we extended the recurrent unit with multiple blocks. Each block has its own flow of information through the time. And there is a routing network which is responsible to softly direct this input to these blocks. As I mentioned before, each block has its own flow of information, so it has its own hidden state. And the hidden state of the unit is the aggregation of the hidden states of these blocks. And as I mentioned before, it's very good to have task-specific and shared parameters inside each component. So here we added another block number 4, which we can call it task-specific task block. Each task has its own parameters for this block. The input to the routing network is the hidden state of the unit at the previous time step, and also the current input at the current input in the current time step. For the routing network, we use a 2-layer MLP, and the output of the routing network will be used to gate the input to these blocks. The architecture of the proposed recurrent unit is agnostic to the internal architecture of the blocks, but only we should make sure that they can control the flow of information. And here for the experiment, we use the GRU as the internal architecture of these blocks. We use the proposed recurrent unit inside the encoder and the decoder of sequence-to-sequence model. Let's see some experiments, results, and analysis. For the experiments, we used English to Farsi and English to Vietnamese as 2 low-resource languages. Here you can see the statistics for the training data. For the English to Farsi, we used TED corpus and Farsi representative language pack from the Linguistic Data Consortium. For the English to Vietnamese, we use IWSLT 2015, which is contains sentences from TED and TEDx talks. For the semantic parsing, we used AMR corpus, which contains sentences from Newswire, weblogs, web discussions, forums, and broadcast conversation. For the syntactic parsing, we used PenTreeBank. And for the named entity recognition, we used ConLL NER corpus, which contains sentences from Newswire articles from the Reuters corpus. As I mentioned before, for the internal architecture of the blocks, we used the GRU, we used Adam optimization, and we applied BP on both source and the target side. And for the evaluation metrics, we used Perplexity, TER, and BlueScore. Here is the result for the model, which is trained with only translation data. This model is not multitask. This is the multitask model, which we use the full parameter sharing scenario. In this scenario, we share a component or not share a component. This is the result for the multitask model when a fraction of parameters inside each component are shared. And here is the result for the proposed multitask model, which has a routing mechanism. For more analysis on the output of the routing network, we computed the average block usage through the time and for the whole test set for the English to Farsi data set. As you can see, the block number 1 is more specialized in the translation and semantic parsing. The second one is more specialized in semantic and syntactic parsing, and the third one is more specialized in named entity recognition. So in this work, we address the task interference issue in multitask learning by extending the recurrent units with multiple blocks. Each block has its own flow of information, and we use a trainable routing network to adaptively share these blocks between the tasks. Thank you.
So we have a couple of minutes for questions. If you ask a question, please come to the microphone or raise your hand. I guess I can start while somebody will ask a question. Yeah, go ahead, please.
Hi, great work. I might have just missed this, but how do you decide on specifically 3 blocks?
Because we share the blocks between the tasks, so we wanted the number of blocks be less than the number of the tasks, but we should try with different number of blocks as well. Yeah.
Okay.
So did you do ablation studies, for example, to see if you train only 2 tasks, for example, MT and NER, and see if, say, the quality of translation improves specifically in translation of named entities?
Oh, for this paper, no. But we have another paper in NACL this year. We did more analysis on the effect of different tasks on the quality of translation. So, for example, we had translation and named entity recognition separately, translation and semantic parsing, and we have more analysis on that. But in this work, no.
So in your previous work, what are the insights?
Yep.
Basically, that would be useful.
Yep.
Okay. Thank you very much. Let's thank Maria again.
Thanks.